I'm a research associate here at Create. I come from, my background is very weird. I went through biology, physics, chemistry, computer science, data science, science education, and now I'm here. Kind of puts me in an interesting position here. And this short talk is going to be, I want to present part of the project that we're working on, that I've been working on for the last 3 years, I think now, which has the very short name, is designing NGSS aligned PBL curriculum and assessment to support students' understanding, engagement, and socio-emotional learning. The first thing I want to say, so I want to cover briefly, as I was preparing this presentation, I had to think long and hard about this because it's a huge project, and just describing all the scopes of it is going to be super long, super boring, and even doing it in a very methodical, like research methods, and it's going to be too cumbersome. So I decided to take a different approach and just show you different slices of the project and focus on the slices that I was mostly involved in, which is curriculum and assessment development. So we're going to talk about, so these two bullets, I promise we're not going to talk about. First two, because I can, by the crowd, I don't think we need NGSS introduction. I do want to talk about what we do and how we do it. So before we start, I just want to, so just before I'm presenting, this project is a huge project with a lot of team members. I think half the crowd here is a PIRE team member to begin with. So I just want to, so there's Chris, there's Ryan, there's Sarah, Quentin, Ichin is here. I think we're missing a few. I think Pang is also on the project. It's a lot of people, a lot of teachers, and the project itself is a very big one in scope. So I'm just the front man for this presentation. So what is the project? So the project is actually named CESE. The funding agency is actually called PIRE. By acronym, we call ourselves the PIRE project, although typically we are the CESE. And the project itself, NSF, multi-year, so 5-year project. And when I actually did the numbers, I had Quentin, the data scientist, kind of go over the number. It dawned on me just how big the project is. Right now, these are the numbers. We're at 130 teachers spread across 2 states, Michigan and California, 170 schools and 8,000 students. Just think about the logistics of trying to measure or collect data, handle materials, handle teachers for 8,000 students. And I think that's where, by sticking to these big numbers, we can make claims that are actually valid. And the goal, and then I took this right from the direction, is to increase student engagement and interest in the fields of science, technology, engineering, and math, so basically STEM. So if you look at this, this is very lofty, right? So it's just one of those, like you could put it on a billboard. Right? So like what exactly do we mean by to increase student engagement and interest? So, and what do we mean by it, and how do we actually prove it? So, and again, we're not going to talk about this. I think you know this. Our beloved rope, I just changed it because I had to change it somewhere because it's always like this. And the 3 dimensions, making sense of phenomena, it's perfectly fine. I don't think anybody here requires extra introduction about this. So when we break down the challenge for this project, you say, okay, we have this new vision for science education. We know what we want to do. So can we articulate like the specific challenges that we want to have in this project? So the first one, again, is we want to foster deep and integrated understanding of important ideas, which is kind of embedded within the spirit of NGSS. We want to engage students, and then I'll get back to that. We want to support students in developing important scientific practices and 21st century competencies. And I always tell this to teacher. I saw this at one of those Department of Education kind of infograph. 60% of the jobs that our students are going to be employees of haven't been invented yet. So it's crucial for us as science education and people who educate researchers and teachers to understand that unless you're building skills, general skills, you're not going to get your students to positions you're not going to get them ready for the science market. And we want to support students solve problems, think critically and innovatively. And again, the first step was to take these big goals, and how do I actually measure them? How do I actually quantify them, and how do I make claims that I can substantiate? So the first one is engage student. Everybody wants to engage student. You talk to every teacher and every science project everywhere. They just want engagement, but then how do you prove it? And how do you prove it within the scale of 8,000 students? So for that, we had to start with developing, we had to start with developing a framework just for the sake of engagement. Again, one facet of the project. So we build on the idea of flow, right, which is a very known concept in education psychology and education. It talks about this kind of intersection between skill and challenges, and we have to be just right. And we add the idea of challenge. So skill, interest, and challenge together. So I tried messing around with a 3-dimensional graph. So you can kind of imagine like a tube in 3-dimensional space. And then it went all over the place. Spend the day on it. And what we talk about, so this intersection between skill, interest, and challenge is a temporal one, which makes sense, as anybody who's ever taught students can never say that students are like this the entire time. If they're like this, they're dead. That's the only time they're like. Students are usually like this. And all over the place. Sometimes they're engaged, sometimes they're not. Sometimes one activity engages them, sometimes we're not. So how do we encapsulate that? If it's temporal quality and it's situational dependent, but we want to still make claims about it, we got to think outside the box. If you do a pre and post unit questionnaire from an assessment perspective, all you're going to get is an average response at best, an average response of what happens in between those. If you do a post-lesson survey, you're still going to get just the average response of the lesson. So how do you rectify that situation? So what we did, and again, not trying to leave. So this is just, before we go, I just want to show you, this is kind of the framework we have for what are optimal learning moments, which is that intersection between skill, interest, and challenge. We have accelerant, detectors, and we argue that optimal learning moments somehow, this leads to science learning and then social and emotional development. But to measure it, I'm just going to go like this. We actually had to come up with a way to measure students in vivo, so like what they do in like a lab. So one piece of the project was getting smartphones, not smartphones, semi-smartphones, just phones. Phones with a screen. Yeah, they're not. No, they're sliders. Yeah. We got a huge amount of phones. We deactivated them. There's no Wi-Fi. There's no data on them. And then we put surveys on them. And the idea is for the survey, as the survey are asking, what are you doing now? What are you feeling now? So students could actually say, well, right now I'm making a model. How happy are you? How bored are you? And that gives us, and there's a lot of advantages for this. The disadvantage, of course, and we can talk about this, is the logistical challenges. Distributing the phones, collecting the data, importing the data, matching the data to a specific student, and aligning it to the curriculum is a lot of work. But the advantages for it is that you actually get samples that are relevant for what the student is actually doing. And the way we sample this, so we have this survey. The survey take, say, about 1.5 minutes to maybe 2 minutes to answer. And those surveys beep or bark. It's an app. It's called Paco. I don't know if you can see the dog that it actually barks. It barks for the entire classroom, and the entire student and the teacher are answering a short survey, and then they do it. So the way we designed it, and again, this is mostly Chris's work, was one of our graduate students. We would signal student in and out of science and in and out of our units. So we were basically using our students as their own control. I would actually ask the student, how do you feel in other classes other than science? And then I would ask them how it feel in what we call regular instruction, but then we would also ask in our units. So then we could measure per student the difference in their social and emotional constructs. That's one big aspect of the project. So when I say engagement, I'm not going to say engagement and then just leave it out there. When I'm saying engagement, I'm actually going to show you specific measures for engagement. So going back to this slide, so we covered this, right? How do we cover these bullets, right? So we have to have a framework. So here in Create, the framework we use is project-based learning, right? It's one of the frameworks. It's not the. I like it. I think it's beneficial. And the features of project-based learning that aligns perfectly to, not perfectly, but aligned to NGSS are the 6 features, which is we meet learning goals, and this time we can talk about learning goals being specific performance expectation. We pursue solution to meaningful questions, we figure out, we do collaborative activities, we use scaffolds and technologies, and we create artifacts. And all those things we can try and measure and collect, right? So when I say this, it's, again, nothing here, that's why the project is so big. We didn't make any assumptions on any component of the project. If we want to prove something, we went ahead, we collected data, we thought about the framework behind it, and we went ahead and tried to prove it. So we have, and this was kind of my trying to kind of show this. So we have this new vision for science education, right? It's there. We use project-based learning as one of the scaffolds for which we created. And now we have to think about 2 different aspects. One is curriculum and assessment. And I put them together because you cannot have NGSS aligned or new vision aligned curriculum but still stay with recall-based assessment. It just doesn't work. Teachers, students, and high stakes players always align to the assessment. So if you want to change, the change has to be on all fronts. And luckily for us, in the state of Michigan and in the state of California, high-stake assessment has been moving in that direction. It is becoming NGSS aligned, so we were happy to move ahead with them. We also want what we call optimal learning moments. So we do want to make sure that what we're doing creates this, which leads to more specific questions. So how do we create units and assessment that align with the new vision? And once we have those, assuming we were able to do a good job, does it actually work, right? And when I was thinking about the goal for this, I was emailing back and forth with Joe, and Joe was doing, as a good scientist, was always pushing back. He says, what is the goal? I'm like, develop curriculum. And then he would email, so what? And I would get upset. It's like, what do you mean, so what? It's crucial. They're saying, no, think about what exactly do you want? What is the goal of this project? Instead of not talking research. So I sat and I thought, well, what do I want? I want students to be able to make sense of the world around them, in general, not in science. I want students to become literate and have the skills to figure out what's going on around them, and I want them to be happy while doing it. And that's how I try to kind of, and it's only because Joe was always keep pushing back, says, so what? I'm like, wow, what do you mean? I got upset on my phone. What do you mean, so what? So, but that's the idea, because that's the goal here. That's really the goal. If we can get, I think we're gonna go basic. I just want students to be happy. I don't want students to alienate towards science, and I want them to see science as something that can contribute outside of the small scope, which is a science classroom or a science test. And I just want them to be happy at knowing that they can do it. So these are kind of our claims.
By the way, he didn't write back happy on the phone, otherwise I would have said, what do you mean by happy?
Exactly. I just put got it. I was on the doctor's office like, what do you mean? So our claims, and this is just a small portion of our claims, and these are the claims that I will try to substantiate in this talk, is that our design process, which I will shortly introduce, allows us to create PE-aligned units and assessment tasks. I'm going to argue that we have a process. It's not a black box. We have a process that allows us to really say that this is what we started, and this is what we ended it, and there's a process for all the steps in between. I want to be able to show that students participating in these units actually develop in their ability to answer 3-dimensional items, which will actually validate our items as well. And again, I want to be able to show that students, as they're doing our units, not only improve in their learning, they actually are happier or enjoy more or engage what we call the optimal learning moments, which is the OLM. And again, my focus in this project was mostly curriculum and assessment design. It's not mean this is not a curriculum project. There's a lot of facets to it. I just want to share the focus on the stuff that I was most involved in. So just as an overview of the units, we went with chemistry and physics. 3 units for physics, 3 units for chemistry. These are the performance expectation that we align. The major one, there's a lot of supplementary one, as Ryan and I discovered as we were revising them. is if you notice, every question, every unit revolves around the phenomena, which is what drives the actual unit. So for example, this sounds too complicated, but basically what we do is we start and we have students put out their hand, and we put 1 drop of ethanol and 1 drop of water. Then we don't say chemistry, we just say, how do you feel? That's it. We don't even, we do the activity without even them knowing that it's a chemistry unit. We're not saying, hey, today unit is going to be this and that. No, we just give them, we just reach out your hand, we put a drop of acetone or ethanol, and we say, what do you feel? And students go, wait a minute, it's colder. But I say, wait, was the container cold? No, it was room temperature. Okay, so why do you feel and how? And only then, after we let them experience the phenomena, we can start talking about, and then I ask this question, which is another non-chemistry question. It's like, if I go outside the pool, why am I feeling cold, right? And then from that, we start working towards these PEs. So that's kind of the common thread for all these units, is we have a phenomena which we try to move away from phenomena that are just confined within the space of a classroom. We have a driving question, and all of this is aligned. So how do we create this? Or how do we create this? So our design process is a big one, right? And to give you a sense of the branches of this, so the green part is the part that we use to develop assessments. As you can see here, it says develop tasks and rubrics. And the blue side is how we develop the units. You would notice that both of them share a common ancestry, which is the part there in like orange, I think. I don't know the color for this. And so first, I just want to talk about the big picture of the process. This one is we use research-backed design process. It's systematic. It's based on evidence-centered design. This arrow is just one of many arrows that I put in. When I say iterative, I don't mean that we do all this, we get here, and then we start asking, are we doing good? There's so many iterative cycles in here that if I try to put in, you wouldn't see the actual figure. Every time we do, we stop and say, wait, what? Wait, and I'll show you what we mean by, more specifically later on, what I mean when I say iterative process, and how committed we are to always ask ourselves the questions, always check ourselves, contrast with data, contrast with interviews, contrast with teachers. But this whole idea allows us, the fact that we have a process and not just, well, it's me sitting in front of the PE saying, this PE is interesting. What can I think of that would make sense? And then I would make up some lessons and then I go. That's the teacher way of doing it. I'm not saying it's bad. It's actually good. That's why we have teachers that can actually do it. But from a research perspective, you want to have a system that is reproducible. We can say, this is what we did. And if you want to do the same, fine, do the same. But if you follow this document, these steps, and you document each and every step of it, it becomes a process that can be reproduced within ourselves and outside. If we share this with somebody else, someone will say, okay, let me try and create a unit like they did. See what I come up with. What are the guidelines? And this in itself already constitutes part of our validity argument, because one of our claims was that we are able to create units that are aligned. One way to substantiate that claim is to say, well, look at this step. Look at what we do. Look at all the steps and measures and countermeasures we're taking to make sure that we do it. So the top of the chart is common to all of them, which I think for us really is the key part of what does it mean to actually design NGSS aligned curriculum. And it is the unpacking process. So when we say unpack, it says here, so we identify the performance expectations, could be one, could be more. You can have a secondary one and a primary one. And then you start unpacking. So I don't have to tell you what a PE looks like. I'm pretty sure you all know what it looks like. But the scope of the PE itself, because it's only like 2 sentences, there's a lot encapsulated in it. A lot. In every practice, in every cost-cutting concept, this is core idea, there's a lot of ideas that are embedded within that short sentence. So if you go into the NGSS website and you click on it, and we can just do this. I just want to do this with you, if I could. I want to show you. So let's take one of our favorite, which is HSPS 1-1, and right? So this is a PE. Assuming this works. It does work. Okay. So this is let's use one of these. These are one PE. And the PE itself is just a sentence. And I'm on purpose selecting this one because that's I think was the most good example of how big the scope of one PE is. Can you really summarize it in one sentence? So HSPS 1-1, this is chemistry. I'm sorry for all the physicists or biologists. It says, I'm a physicist, so use the periodic table as a model to predict the relative properties of elements based on the patterns of electrons in the outermost energy level of atoms. It's one sentence. But you can't tell me that you can look at that sentence and say, well, let's develop a unit. Let's just come up with some lessons and ideas and come up with a unit. I mean, you could, and I'm pretty sure some people are, but that's not how we develop it. Think about all the things that have to go into understanding every piece of this. So what we do in the unpacking process, and it's a very well-documented process, is we go and we actually, and if you click on it, which is nice actually, it's NGSS makes it very easy on you. So if you look at this, and so this is the practice, and if you look at like this one, if you click on it, you should be able to, I don't know if it's working, but you should actually get to the actual framework. And then you can actually read the book and say, well, this is all the stuff they made. And then we say, well, what's the practice? The practice is modeling. So fine. So I think I know what modeling is, but is that going to cut it? No, it's not. What does the NGSS constitute as a model? What is the expected level of high school student when they make model? Where are they starting from? Where should they end? It's all these tiny steps that we do for every single PE that we align our unit to makes us more proficient in really understanding what is needed. What are the ideas kind of embedded in it? And it takes a lot of time. And again, the process is not, what happened to my, oh, it's here. The process is not one and done. We always end up that we unpack, we get to the actual unit, and then we start thinking about the unit. We say, wait a minute, I think we misunderstood this. Let's go back to the unpacking, unfortunately. It's never fun, but we have to do it. So there's a lot of like small circular lines that go here as we do it. So let's assume we did it. Let's make an assumption that we figured it out. And now we have to branch off. And we branch off into the assessment development, and we branch off into the unit development. So now, ideally, why would we branch off instead of putting this after this, right? Why doesn't just make it sequentially? Unpack, develop a unit, and then develop an assessment, right? It works, but it has one big downside. We want to be able to claim that this evidence, this assessment, provides evidence not to the proficiency of the unit, rather to the proficiency of the PE. So that I can take my assessment items and say, here's my assessment item. If you teach any part of HSPS 1-1, take this. This should cover what you teach, regardless of the context of what you're teaching in. So that's why we separated it. Now ideally, and again, another flaw of the study, we would want this team to be separated from this team. Because we don't want, as we're working on them, we don't want to bias the units. Fortunately, we don't have that many personnel, so we ended up working on both, which is very hard. How can you write an assessment task when you already wrote the unit or are working on the units? How do you not bias yourself towards it, which is another big issue? How do we prevent bias? So we have this part and we have this part. I want to focus on, I want to show you just a little bit of how we create a task. And it's going to be physics, so enough chemistry for now. I just want to talk about a little bit about kind of what we do here. So if you look at the steps here, and again, very iterative. We brainstorm phenomena and the driving questions. We develop learning task sequence, which is we took the PE and we break it down into like sequential parts of what we want to achieve. And then we develop our evidence statements and learning performances, and then we go through the lesson plans, and this always kind of circles around. And then by the end, we should have ready-made units and assessment. They go out for review. If needed, they go back up all the time. This is year number 4, I think, of the project, and we're still in revision all the time. So part of the responsibility we took upon ourselves is to not say, you know what, it's done. It's too late in the project. This is what we have, and this is what we're going to come up with. We're not. Every time we find some issues, we get a comment from a student, from a teacher, we go back to the design board. If needed, we're willing to scratch everything and start from scratch, because that's how committed we are to the process. And we're not even though we spent countless of man hours on the units, if they're not good, we just gotta redo it again. Yes, Bob?
Will it upset your flow if I ask a question of this?
No.
So if I'm understanding this process correctly, you're starting with the PE.
Yes.
So you're not starting with the phenomena, you're not starting
No.
with the whatever. So you're focused on just one PE?
So depends on the PE. That's a good question, because some PEs, like the chemistry PE, HSPS 1-1, are huge in scope. And the fact that you can just focus on not all PEs were created alike. Some PEs are more so. The physics PE, for example, one PE is Newton's second law. It's develop a mathematical model to understand the relationship between an object's mass, velocity, mass, force, and acceleration. That sounds doable within one PE, right? Some PEs are larger, so we can only take facets of the PE. We say, well, this is a big idea. We can only cover X amount of ideas when we do it, when we unpack it. And sometimes we need supplementary PEs, right? In chemistry, how can you talk about anything in chemistry without talking about energy, which is one of the PEs? How can you talk anything about interactions without talking about forces, which is another PE, right? So during the unpacking process, and when we start really thinking about what students need to understand, we always have to take like ideas from other PEs. So we would have what we call a bundle. It's not really a bundle, but we can have like one major PE and two supplementary PE that kind of support the ideas nested within the first one. So it kind of differs between them. That's why the table I showed you sometimes have 1, 2, or 3. And so 1-7 is a big one. And it has supplements. So for example, electric motor, they have supplementary PE because it's an engineering focused unit. So we have to have some engineering PEs embedded in it.
These are also shorter units.
Yes, these are 2 to 3 weeks.
Right, so depending on the length of the unit, you're going to be able to bundle
More
things together. And like Izzy said, in electric motors, you're not covering all of them, you're only covering parts of them.
Right.
You're not covering the whole PE. You possibly can't do it
In 3 weeks. So the language we use is we're not saying we're covering PE, we're saying that we're building towards mastery of that PE. So we try to kind of hedge ourselves in saying that we're not going to cover a PE in 2 weeks, we're just going to build towards it. We're going to create some general ideas, understanding within the students towards that PE.
So the expectation would be that there would be future units that would also address or build on that understanding and continue to move the students toward.
Yes. So if we had our way, and our way means $5 million, I would say that give me a whole year of physics, high school physics students, and then let me decide, and I'll make sure that we build everything towards, and I can say with like a full conscience that this is mastery of one PE completely. Right now, within the scope of our unit, we can only provide 3 short units, so we can't make those claims. I wish we could, but giving enough time. And so using this process, yes, if you had a whole year of curriculum, you should be able to claim mastery of specific PEs. You can say that this year, sophomore year, junior year, we're covering these PEs completely, and you can test it. That's
picking the PEs to begin with?
good question.
Did the teachers have any influence as to which ones?
So there is, and this is a really good question. There is, so teachers already have kind of what the stuff they teach, right? So if you're a chemistry teacher, even though you went through NGSS or you went through whatever iteration it is now, you have topics that you want to cover. So we try to not interfere, not take like out of left field kind of topics. So for example, for physics, I know that a physics teacher would have to cover Newton's second law, regardless of what he teaches. So choosing this PE, HS 2-1, was a given, right? Electricity is the same thing. So we took topics that are expected to be covered regardless of what curriculum you were doing, and then just use those PEs, right? And the units initially were co-developed with teachers, so we had the luxury of working closely with teachers and say, well, this is what I cover, this is kind of the amount of time I take, this is what I expect students to be able to do. So So I just wanted to show you just a short glimpse into the process highlighted in green, which is after we did the unpacking, how do we actually develop a task or try to develop a task, and how do we validate it, which is kind of the most interesting part. So, and again, tip of the iceberg. This project is humongous. You could spend 5 hours just talking on every methodology piece and process. It's not the aim of this talk. It's just to show you just kind of an overview of what we're doing, and then so you guys could appreciate the work we do, I think. So this is the process. I just took the process and I tacked it there, and I highlighted kind of the phases that we are. So for this one, again, I'm a physicist, so I'll go with physics. This is the PE. So for example, Bob, to answer your question, if you look at this PE has electric fields in it. This specific unit we developed did not have electric fields. We did not build it towards it, which is fine. That's why we gray it out. We say, okay, we're not going to focus on the entirety of the PE. These are the pieces we use. That's part of what we do, because PEs are very big in scope. So this is the PE itself, and then we move on to the unpacking. So this is from the actual description from the NGSS. And if you click on this or this, you immediately go to the framework where you get much more information about what exactly are you expected of this, what is expected of the students at grade 8 and at grade 12, potential issues, and then you can go to the research and actually find misconceptions aligned with those DCIs or cross-cutting concept, and that's kind of the work we do. So once we do that, one thing, and again, this is going to make sense for the physicists here, but we create what's called concept maps. So we take the big ideas, and again, it's the big ideas in the PE, not the big ideas in the unit. We're not thinking about the unit. The unit is something else. Theoretically speaking, someone else made the unit. I'm making an assessment for the PE. And we create these ideas, kind of the threads along what we think the PE encompasses. So for example, these are the 3 ideas that you can show. And again, this doesn't have to be like a physics lesson, but we can talk about objects that interact through a magnetic field, and then there's force that affects the shape, position, and there's also energy. And these colors will kind of denote specific strands of thoughts that we have within the scope of that PE. So once and this comes from actually reading the DCIs, reading the content behind it, and designing and figuring out how does it make sense to kind of graph these ideas. And these paths become what we call task learning performances, right? So it's color-coded to match these kind of flow of ideas. And every learning performance is 3-dimensional in nature. It means that it has a practice. It doesn't have to be the practice set forth by the PE, but the PE it has to be 3-dimensional, right? So we have developing model, we have analyzing patterns, we also have patterns here. Everyone has a DCI and it matches to this. And only then can we start thinking of the actual task. It's not vice versa. I don't come up with a task and then try to align it. I just say, well, now that I know what the task is, how can I design it? And these are our evidence statements. So for example, if I claim that students should do this, what evidence am I going to accept that will make me say, yes, they did accept this? So we create this. This is all before we even wrote one sentence of the actual test. We go through all this trouble just to do this. And then we come up with a question. So for example, this question is a very simple one. Some students played around with magnets on the fridge, and some of them attracted and some of them repelled, which is not a very interesting phenomenon. But the question we ask is not simple, and it's not very physics-like. It's not going to be what a physics teacher naturally asks. We say, draw a model to explain why in the first observation the bars move further apart, while in the second one they got closer together. And we actually add some clarifying statements, say that in your model addresses the force and shape of addresses the field and the force involved. So we act that. So this is one question within the task. And we have a rubric. A rubric is a 3-point rubric. We have our evidence statement, and we have the proficient, developing, and beginning level, and exactly what student needs to be able to do. And I want to show you what it looks like. So I talked about the task validation. So I put this logo, and let me just, before we do that, I just want to show you. So we create assessment task, we do content validation, and then we do cognitive interviews with students to make sure they understand what we want. And then we take that, and we revise it. And then we add student responses, initial one, and then we have statistically valid scales. And then this keeps going and going and going. And to add that, we even, so Achieve, for those of you who don't know, which I assume is everybody, everybody knows this, Achieve had an initiative to say, you know what, give us your assessment task and let us give it to outside judges who would look at your assessment and say, these are good as or not. We said, that sounds like a great idea. And I'm not saying it sounds like a great idea because our unit, our tasks got flying colors, they're passed. It's not. We got really good feedback on it, which is fine. We're happy with it. It's like we got outside feedback, which again, just contributes to the validity argument of our tasks. So I don't have a lot of results to show you. I do want to show you a few results. So this is from one unit. This is the same unit I was showing you. It's one item, one class. And this is the distribution of scores between beginning, which is the blue, proficiency, and so basically 1, 2, and 3. And this is a pre-post design. And as you would expect, nobody was proficient before, which is fine. And most of them were lumped into the 1. And after the unit, again, just a 2-week unit, you get this. And what I like about this is that it's not super exaggerated. They not all became amazing physicists within 2 weeks, because that's not reasonable. But it is a shift. And if you want to talk statistics, 2 of the tests we use, chi-square and man-u, show significant results, even within such a small scale. And we can see improvement. And when I mean see improvement, I can also say, this is the improvement we see, right? So this is the same student, pre and post, 2 weeks. This is the model he made of magnets before the unit. So I don't know how many of you are physicists, but magnets do not have a plus and a minus, right? And the same student, after 2 weeks, drew this. Now, this isn't perfect. There's still some issues here. But as a qualitative example, I think it shows nicely that, so for example, these are forces and these are field lines. There should be a designation of what is force and what is a field line. But still, here you can see a much more deeper understanding of the idea of not that magnets attract and repel, but what is the shape of the field between them that contributes to that effect, which is, for us, is a very good sign that we're on a good direction. Another aspect, and this is, and again, pardon me for the statistics, so we said they do good, but are they happy? So these are results from the ESM study, the phones we gave them. And these numbers, and again, for those of you who are not familiar with logistic regression or odds ratio, this basically compares within our units and outside of our unit. And the bigger the number is of 1, it means that there's higher percentage that this would happen in our units rather than the original sign. So for example, a 2.14 odds ratio means that students are 214% more likely to experience optimal learning moments in our prior units than they're in the regular science instruction. So for example, you can see, so this is significant, this is almost significant. You can see an increase in optimal learning moments, imagination, and solving problems with multiple solutions. This is based on student reports, right? And again, from having, and this is just one class. So the fact that we're able to show significant results with such a small sample size also contributes to the effect of it, because usually it would take a much larger sample to get this response from an odds ratio. It's such a small class. One final result, this is another physics unit, and I don't want to confuse you. I just want you to see the colors. Just think of it qualitatively. The green is the proficient, so you can see not a lot of abundance of green in the pretest, and a big abundance of green in the post-test, and the same thing with the red. And again, I don't want to, this is not a statistic talk, but these are statistically significant results, all but 2 items. It's the same thing, a single class, 25 students. This one was, just want to go back. So this one was mostly African-American students, this specific class. This one was mostly Caucasian students, which again, brings the issue of gender or ethnicity that we have to take into account, another data point. Also below state average in science scores, and this is the entire task. 4 items with separate sub-questions. And you can see a marked improvement, and again, it is statistically significant. So I want to go back to my claims. And I know it's just preliminary results, and I know we have a lot of data to support this. But these are the claims, not my claims, it's our claims, that we are able to create these units, and these units do well in improving student understanding, and they do well in improving student engagement. So the future. I really like this image because it shows exactly what we just have tons of data. And it's like, I know Quinton and Chris and Sarah can talk about this. There's so many facets and so many ways we can collect data, and all these questions we can start dissecting. Because we have student level data, questionnaires, pre and post, background surveys, summative tests to kind of establish science background. We have all that data, which we can start asking all these big questions, like how does gender, ethnicity, socioeconomic status, English language learners, as I don't know if many of you know, but schools in California have a high percentage of Hispanic or Latino students whose English proficiency is very low. So we have to, how does that affect their engagement? And it's like we're also dipping into machine learning, because how are you going to score 8,000 tests, right? So now we're working with fine people at Acer trying to help us. Can we use machine learning to score some of those constructed response? Can we make this a valid tool? There's a lot of facets that can be covered and will be covered within the next year and a half. And again, I want to say thank you for everybody at the team. There's a lot of people involved here. Some of them are here, some of them are not. And thank you. And I really like this, yeah. So, right? I was like, yeah, this is what I want. Questions, issues, ideas? Yes, Dave.
A wonderment.
A wonderment.
Yeah. So.
Yeah, my hair is like this all the time. Yes, I get it.
No, yeah.
So.
From like socio-emotional learning theory perspectives, tools are as good as the user, right? So you can have the best curriculum in the world, you can have the best units in the world, but it matters how people perceive and use it. So I'm wondering if you can talk a little bit about the classroom context or the work with teachers that makes this possible.
Right. So
it's fascinating that the kids feel better or happier, but I could also imagine the opposite scenario of I'm going to give this to a teacher and it goes awry.
Right.
So like, how do you support the teachers? How does the school support the students as they're doing?
And again, when I showed you the tip of the iceberg thing, so professional development and the way we work with teachers is a huge aspect of, first of all, our time and our work. So when we work with teachers, not only do we have like PD sessions with them, we work closely. We have like weekly Zoom meetings where we meet with them. There's just the process itself is just like because you're right. And then we found some data. For example, we had a wonderful physics teacher, wonderful, but he just didn't get the idea behind the modeling tool we were using. And because he didn't get it, naturally his student wouldn't get it as well. And he was an amazing teacher. There's nothing. It's like one of the top teachers we ever worked with. It was an issue. When then after the first year, we said, wait a minute, we messed up. These students are scoring very badly on this. They don't like modeling. We can see the data. We say, wait a minute, so something's wrong with us. So we went back, we revamped our PD. Instead of saying, okay, enough talking about modeling, we let them engage with it. And then we see that some teachers chemistry teachers from some other states are afraid to do the experiments we're giving them. We're giving them the materials. They have the equipment, but they're not proficient enough. It's not our fault, so to speak, but it's something that we have to support them. So again, we revamped our PD, so now that we're actually doing the labs with the teachers. There's so many, and you're right, there's a big variable in between us, which is the teacher, that we try to support as much as we can. It's never easy, and especially working with 130 teachers, you're gonna get a population of it. But we always tell our teachers that, exactly what you said, all the materials in assessment don't mean anything unless you're into it and then you buy into it. So yes, we consider the teachers our prime resource. So yeah, it's exactly what you were going to say.
So our professional learning program, as is important as everything that he talked
Yes.
about. So he presented two parts of the model, the curriculum materials and the assessment, but the long-term sustained professional learning is as important.
Yes.
And it's part of the model. He just didn't talk about it. So it's,
right.
It's not a separate part. In fact, next year we're hoping that we can do a maturation study, because we're going to be able to follow these teachers another year, right, where they get more professional development, which will make all the difference. So we're not just developing curriculum assessment.
No.
And we realize that given such innovative, challenging materials, it isn't going to happen unless you have a really rich, integral professional learning program.
Right. Yeah. Yes.
I just, you only showed one snapshot, so I don't know if it's representative or not.
Yes.
So my question is about the, I think it was the assessment question
Yes.
that you have there. So in considering the tasks and the assessment, are you taking into consideration about not perpetuating certain stereotypes or biases? Because the question you showed us was a physics question, and it was about Tom and how he did something. And
Yeah, oh, so we actually did. What you're seeing is actually one of the earlier version. So we do apply equity and fairness, and the example I showed was actually the only example we have of a male person. Everything else is actually girls. So the assessment for force and motion is actually about Sam, she likes to ride bikes, and then she thinks about what's actually inside of a bike helmet, and then she started to do experiments. So we actually do think of those things, and that's why. And sometimes you say you think, but then because you're so busy with doing it, so it's good that we have Achieve. We send the assessment to Achieve, and then Achieve, when they have this really big rubric, they say, is this applying, DCI, CCCs, and SCPs, but also equity fairness? What about like giving some that's like stereotypes or just like that? And it's crucial because my specialty is not equity. So I acknowledge that, and we seek outside help, and we seek outside revisions to exactly address that. We were talking about some of our items needed to be translated to Spanish, and then we had to consider equity issues from a Spanish-speaking perspective, which is a whole different ballgame. We don't shy away from challenges. We accept them, and we say, I was happy. Some of our revisions for Achieve are not spectacular. I'm like, fine, thank you. Let me make it better. And that's the mindset we have in the project. We don't shy away from something that doesn't work. We say, yeah, fine, let's fix it. We have the expertise. Bob.
To the magnet assessment response?
Response, the model? This one?
Right. So if I remember the question correctly, it was simply to construct a model to explain the
Right.
phenomena observed.
Right. There's also a description attached to this question, which I didn't share.
Okay.
So a model for us is always the model and the explanation that comes with the model. And those are interchangeable from us. So let's say he didn't address one component here, but he addressed it in the written explanation, we take that into account. We don't expect the model to encapsulate everything, right? So the model without an explanation is just a drawing, right?
Okay, so this was a piece of my question, right? Because in this context, right, you could say, I could try to explain this thing, and what I'm really asking is how much weight in your assessment of the students was placed on a canonical understanding versus a model that was functional, right, if not canonically correct, but it worked well for the particular example. So for example, over here, right, this notion that there are
pluses and minuses, yeah.
plus and minus magnetic charges, right?
Right.
Is a perfectly viable model that can accurately explain the phenomenon in question, right? It's not canonical because we call plus magnetic charges.
Right, and there's no such thing as a magnetic monopole, right? So the big differences between, and that's why we make an exception of it, is that in comparison to electrical charges, we can have a plus side and a plus and a minus separately. Magnets do not have monopoles, right? You can't have monopoles, right?
Except that in electrical charges, we all know that things are generally neutral, and when we have pluses, we create a minus.
But still, right.
The same way. Right, so this is my question, right? How much are you weighting what could be a completely valid model, right, for the phenomena observed versus how canonical it is in terms of...
Right, so it's a good question because I think...
So to follow up on it,
right.
So another example would be, it's a perfectly viable model to be Newton and assume that there's a force at a distance.
Right.
You don't need the intervention of a field, right? And so if a student comes up with a model that's a force at a distance model like Newton, right? Is that downweighted, or even though it's perfect? I would say that because this assessment is three-dimensional, we want students to arrive at a specific DCI or a specific strand of the DCI, which is specified by the NGSS, which is that's the standard that we align ourselves to. And the standards set forth by the NGSS or the framework specifically say that while the idea of force field was true historically, the DCI that we want students to achieve at is the idea of a field exerting force at a distance and not force, right? Not force at a distance. So we do have some leeway for creativity. So when we score, and this said Sarah here that scores the stuff with us,
when we see some out of left field question that is very creative but not exactly, we pause and say, wait a minute, can we learn something from this? Can we expand or change or modify our rubric to say something, right? So what happens if a student gives you a model as a graph, right? I'm gonna, that's what we had somebody. Instead of giving a model of drawing something, they actually drew a graph. And the graph was actually correct. Not for this question, for another question, for Newton's second law. We said, how does the ball squished against the wall doesn't squish as much because the wall has foam on it? So a student gave us a graph that says thickness of foam, force. And then he just did like this. What do you do there, right? So it's not specifically what we wanted, but it is correct. So all the time when we encounter those kind of weird ideas, we always have to go back and make sure we kind of give ourselves kind of an honesty check and say, well, is this a good answer? Should we accept it? And if so, how can we revise the rubric to be more holistic for that approach? And it's not easy. Think about 8,000. We have like 3,000 answers of this. We have.
So you are looking for canonical explanation.
Yes, because we are aligned to NGSS, and that's kind of part of what NGSS alignment kind of means.
So Bob,
Right.
another way of thinking about your question is if I was this classroom teacher, right, and I looked at the pretest, that's a wonderful thing to build off of. I would love it, right? I would definitely use it. But that's not with the purpose that Izzy introduced us for, right?
Right.
This was for the purpose of showing how we move, how kids develop more towards the PE, or in your case, you want to call it canonical understanding. So we want to know where they were and where they're getting to. So you're right, that's a wonderful model, just a beautiful model if I was the classroom teacher to build from it, right? It's not right, but it's limited. It's going to break down eventually. And from an instructional standpoint, that's what I would want to do. And I'd want to move them towards that thing. Izzy was not showing this as part of instruction. He was showing this as what the kids come in with and what they
Right.
end up as.
Go back to this. Just like this. Any other questions? Are we done with cookies? Thank you so much for your time. Wonderful. Wait. We have time.
We got time, guys.
Is that people? No, I always want to keep this. Yes, Melanie.
So I have a question about your periodic table.
So wait.
Yes. Process, task, what specific? I mean, do you want me to go back to the design?
I want to go back to your driving question.
Oh, okay. Let's go here. Yes. Which one? Here?
Yeah.
Yes. Okay.
So
I like this.
the driving question requires you to know almost all of chemistry, right? You can't answer that question.
Which is a good question because, and we have evidence to support that, we have been struggling, and I feel honest to say here, this is not a pretty, we have been struggling with this question/unit for literally, Ryan is not joking, several years. We have been having meeting after meeting, and it stems from our idea to not accept things at face value and say, well, you know what, it might work, but it's not going to cut it, because it's like, there's toxic. What does toxic mean, right? So it's a phenomena, but students can understand toxic, but what does it mean from a figuring out process? And we came around, and I agree, this question is we're always thinking about revising, always messing around with different ideas, because, like you correctly identified, there's always issues with what we try to achieve. I agree.
So, I mean, this PE about periodic table is a cumulative PE. It's one that really encompasses all of chemistry.
Right.
And to say,
Building.
we're going to cover this in 3 weeks.
No, because I specifically said building towards it. So we have specific facets. So when it says,
The driving question says that you're going to. I guess I'm just worried about this approach where a lot of these P's I don't think were really intended to be taught as a unit, right?
right, so that's why, as part of our revision process, we kind of came to the understanding that some PEs are not even PEs that you teach, they're always there. Like PEs of 2-5 and 3-4, forces and energy, are always there. So now we kind of brainstormed it and we said, these are the cross-cutting PEs that we're going to have. So this is going to actually go through revision about making those PEs a cross-cutting PE. So we're always looking at things with forces and energy perspective. And that's why Ryan keeps...
That's true.
So we can't, and that's the conclusion we can. That's why we have Ryan, right? That's fine. But so that's what we appreciate this. So we literally had a meeting not a week ago where we actually drew the PEs and then said, wait a minute, P 3-5, 3-4, 2-5 are actually applicable to all of them. So part of the next revision process, which we need to find time, is going to do that. Because we're not settling for what we have, not at all. Our goal is to always push this. And this one has been bugging us for a while, literally years. And we always try, we talk to teachers and we try to come up with ideas and we consider student prior knowledge and say, well, maybe they need to know more. Maybe we should put it. Maybe we should teach it. But then the unit becomes too big. There's always these kind of pros and cons that we kind of weigh. But yes, your feedback is spot on. We do not think these are perfect. Far from it. But we are acknowledging the need.
So you're absolutely right, Melanie. You can only get parts of this. The question is, where do you start? Yesterday we were actually talking about getting rid of PS 1-7.
Yeah.
I think we're putting in PS-14.
1-4, yes.
And the question then becomes, well, should that one come before we do the PR cable one? Because it's building from that other knowledge we were just talking about, right? So it is this real iterative process of how you're trying to...
And keep that in mind. We're year 4 of the project, and we're literally sitting in a meeting, and we're talking about completely scratching one unit and heavily revising another one, right? Which is not something, as a curriculum developer, is not something you want to hear when you have basically the next PD is June, so we have 2 months to actually get our stuff together and actually revise it. But we're not, that's part of the game, and that's how we accept it. So yeah, listen, like we literally talked about getting rid of this unit because 1-7 is too much. And changing PEs because this PE doesn't work. If it doesn't work, we'll switch it. We're always, it's like we're not afraid of it. Bob?
I think the part Melanie's getting a deeper kind of concept here, right? And that is the thing that I originally raised, which is this notion of starting with PE as an instructional focus, right? The PE is really an outcome measure. And if you think about what a learning progression is to achieve a particular PE, for some of these bigger conceptual PEs, right, so it's this longer term kind of thing that you would build over the course of a year or 3.
Right.
And so, you know, the interesting question here is, you know, a deeply kind of theoretical one is, are you hamstringing yourself a little bit by building instructional units so tightly aligned to a PE when we know that to build the understanding for the PE is going to proceed across multiple instructional units, you should really be building a learning progression that goes across multiple instructional units using a variety of different phenomena.
Right.
Right. So is that you know, is that initial choice perhaps hamstringing the effort?
So we are constrained by one thing, by the study design, that we can only get into classrooms for 2 or 3 weeks at a time. Within 3, that's kind of what we were able to do. And I think that because we're doing the unpacking, and because we're not just taking the PE and say, hey, let's do this and be happy with it. Because we do thorough unpacking and we look at all the ideas, we actually, so you described like a big learning progression towards that PE. We have that view in mind. We're just chunking it off. We can say maybe we can only do the first 3 miles, right? If it's like a scale to 10, maybe we can only do this. So when I say, and again, maybe we should rethink the way we describe it. It's not really aligned to a PE, just one, because there's so many ideas, right? Maybe we should think of a better way to kind of describe, you know, cross-cutting ideas that always kind of, you know, permeate all our units that are kind of several of the PEs. Maybe we should not describe it specifically as PE aligned, because then people think incorrectly so that this unit covers this PE. Maybe we should think of a way to kind of measure. But I still think that starting from the PE and working to expand it is still the way to go. It's just there's some constraints that stem from a 3-week unit that we have to mitigate. I just think.
If you would imagine, right, so you've got, you know, looking at this list, you've got how many units that are chemistry focused?
3 and 3. 3 chemistry, 3 physics, separate.
9 weeks is a pretty substantial chunk of the year, right? And if you look at that and you say, if we were to keep building this way, would we really achieve by the end of the year all of those PTs, or would they be this kind of isolated focus on individual PEs that wouldn't build that understanding thoroughly over time, right? That's my question. Whether your initial choice, because of the constraints of this particular
study
experiment, right? Whether you're really building toward a full curriculum, or whether you're really just testing these things in isolation.
I think the results show that ideally I would want to take this and make this into a full-year curriculum. I don't want to be constrained by the design of this particular study. I feel that if you give me enough time, I can fill in the gaps like Melanie said. I can fill in this gap and not make it a 2-week unit, make it a full-year endeavor, right? I can take these units and I can start spreading them out across the PE spectrum that you're supposed to cover by, administrator. You're supposed to cover X amount of PE. I can take it, spread that out across the year and see how do I build from A to B. And I still think this is a valid way to go about it. And I think that we're always struggling with the constraint of time, because we always want to build, we go back and we say, well, let's develop this idea, right? For periodic table, they need to understand forces, constructing within an atom. That's a whole issue, right? Melanie.
So I just wanted to comment on that, because I think that I agree with Bob greatly, and I think that this is the point of the core ideas, right?
Right.
They're core, and they have to be in everything that's everything that you teach has to be connected to them,
Right.
not just one. And this is particularly true in chemistry. They have to be connected to many of those core ideas.
Especially with forces and energy, exactly.
Indeed. And so I'm just worried, again, I just want to emphasize that I'm worried about this approach because it seems fragmented.
So again, no one made a claim that taking this 2 to 3 week unit, that they're going to come away with a full understanding of it. That isn't the idea, right? It's sort of an introduction. In fact, it's more of an introduction to some of this than anything else. But it's to get kids to wonder, like, what's going on here? Why is this thing so reactive and this other stuff isn't reactive, right? So it's beginning to build a model, and it's certainly, and this is why I said if they had PS-1-4, maybe they could get further. And if they really had a good understanding of some of the energy ideas, maybe they could get even further, right? So unfortunately, we didn't have that luxury, right? So while I agree with everything you said, we didn't have that luxury. And I would love for someone to say, here, Joe, here's $10 million, develop a learning progression for high school chemistry and high school physics and go build this thing. It'd be wonderful. I'd love it.
Right.
So if you can think of a foundation that's going to do that for us, let me know. I'll do it together. But that's what it's going to take, right? I mean, it's not an easy process.
Yeah, even these kind of short units that are limited in scope take an insane amount of resources and work and literally years of development. This is an ongoing process. This is like 4th year. This is like years in the making, and we're still struggling. So I agree. So if you have $10 million, yes, please.
But again, I wouldn't take that, even though it looks like they're meeting all those PEs by these units. That's not the case.
Yeah, we specifically
The
say.
cases we're building towards it, and in fact, in many of them, you're only covering portions of it.
Right, because we can.
This might be a bad representation.
Yeah, maybe we should just describe the components within the PE that we're trying to achieve.
I mean, I would also argue that when you look at going back to the PEs, it's not what they do at the end of one class, right? It's actually what happens at the end of one year. So you're going to get a better understanding of many of these PEs, not just in high school chemistry, but it should through high school physics and through high school biology and through high school earth science. A lot of these things mix with high school earth science. So these are supposed to be things that are measured at the end of high school, and these are not, well, as you all know, I'm not saying this to you. These are not high school standards, right? These are standards that should be met by the end of high school, and that you should learn these, that kids should develop this understanding
Throughout,
as a result of all your coursework. And one of the things we've done mistakenly in high school science is we don't do some of that stuff, right? I mean, particularly the energy PEs. You never, for some reason, if you're in earth scientists think kids understand energy. So we talk about climate and weather, which all is related to energy. No one ever talks about energy and all that stuff, right? So, so you're absolutely correct, right? These things, the development of these ideas don't happen as a result of 1 2-week unit or 1 3-week unit. It should be a progression through all of the 4 years of high school.
Yeah. And I just want to say that I think chemistry in this perspective offers a much greater challenge than physics. The scope of ideas, and we had this issue with Ryan, when we had this discussion. With physics, it's much more easier to encapsulate several facets of the idea. It's chemistry, it's almost impossible. One would argue it is impossible to actually talk of. Okay, any other questions? Good.
Since we have time, I'm going to be grossly speculative here. Right?
Yes.
Because one of my concerns about the structure of NGSS, right, is that the PEs channel things a little too aggressively, right? So really, if we're trying to build off the framework, we're trying to give kids experience with modeling in a whole variety of three-dimensional contexts over time, right? There's really kind of a learning progression toward modeling and toward each of the DCIs and cross-cutting concepts and things. You know, what's happened with the PEs is they pull out these isolated things, right? And if people focus their instructional efforts in the way you have on the individual PEs, right? I'm not necessarily convinced that builds a proper learning progression toward what we're really hoping for, because those PEs were built in isolation a little bit, right? They were, if you look across the PEs, they don't necessarily hit each of the practices with the same amount of
Weight,
time and
yeah.
effort, right? For each of the DCIs and things. And you know, they were necessary because the core purpose of the PEs was for building assessments in the end, right? And assessments you inherently narrow, right? We don't test everything on our test, right?
Right.
We choose some things to do. But I'm wondering if building instruction off the PEs, right, is really suffers from the same classic problem as teaching to the test in other ways. I'm just kind of curious as to your thoughts.
So my thought is that even though the PE are like points, you can, and I only have geeky metaphors because I'm a nerd. It's like principal component analysis when you take like, I'm sorry, that's kind of my metaphor. So you take a lot of variables and you kind of summarize it into like focal points, right? That's what PE is. So it takes a lot of dimensions and you reduce them. I agree. I want to argue that our unpacking process does the opposite. So if you give me all the sets let's play it the other way. If you give me all the chemistry PEs and you give them to me and I unpack them, I should theoretically get back to the entirety of the framework. Because even though they kind of shrunk it down and isolated it, when I unpack it, I go above and beyond. So I expand it, I re-expand it, and I actually do encapsulate all the stuff that because I do consider supplementary ideas, auxiliary ideas, what ideas students need to know in addition to what other ideas from other fields can actually help them. So our unpacking process, I would argue, re-expands those points. That's why we're not aligned to the PE. We're aligned to the framework. Maybe that's how we should frame it. We should say that we're not aligned to PE. We're aligned to the spirit of the framework that was expressed through these kind of 4 ideas. Maybe.
Right. So that's a very good. Why not start with the framework then, as opposed to start with the PE? If all you're doing by unpacking is getting back to the framework, you put in an enormous amount of effort to reverse engineer
something that's
started with the beginning.
So Bob, you know as well as I do that standards are a political process.
Exactly. I was going to say
You're
that.
leaving that out, right? So these things are written totally for a political purpose to support standards. When you're to support student learning, so states can measure something. When you're designing curriculum, you do something totally different, right? You don't, right? So when for us, even though the PE might say develop a model, the unit does not focus
on just that.
Developing a model. In fact, it's almost impossible to develop a model if you weren't involved in some form of data collection and
analyzing and patterns and investigation.
Design it from, right? So designing instruction is different than meeting some political outcome that's over here. And so, Izzy didn't bring this up because you limit the time. When you're designing instruction, we take out the practice, we take out the
cross-cutting concept.
Cross-cutting concept and the core idea, and we purposely mix and match what fits best there. Right. So the standard might say develop a model, but we say, oh, we got to start off first by kids have to plan an investigation, and then they have to analyze data. Oh, now they're going to argue a little bit. No, then they're going to design a model, right? So that from an instructional standpoint, that's a different process than a political thing, which is coming up with that standard.
Right.
I think that's my point, right? So my question is then, in terms of your process, why not acknowledge that and proceed instead of from the PE?
We do acknowledge it. We say it all the time. I just did, right? In our design process, we do not just do the modeling. If you look at any one of the units, although the PE may say design a model, that's not what the unit's about.
Right.
We acknowledge it clearly.
But I think for,
Every talk we do.
Right.
And writing about it, it's acknowledged.
but if you wanna, so what's the dream scenario for us? Let's say 1.5 years from now, this project is out of IRB and we can distribute the units for everybody. What you would, from like Joe said, that because people are all concerned about standards, because standards lead to assessment and assessment lead to teacher evaluation, what is the best way for us to distribute these units who we know are actually aligned to the framework? If I go to you as an administrator and say, well, we have these units that we kind of wrote when we read the book of the framework. Or I come to you and I say, hey, Mr. Administrator, I have units that will help your teachers meet the standards set forth by Michigan Department of Education. It works. I mean, I agree that there's always issues. It's like, as long as we know that we're not doing standard alignment like they think about it, I'm happy with it, right? Even if it's colored differently, I can live with it, because we have to, there's always this assessment, alignment, like weight that is rested upon teachers and upon administrators, and we have to acknowledge it. If you don't acknowledge it, you're not going to get acceptance of the work we do. It's just part of the game, I think.
But there's a difference between starting with it, right, and ending with it. So in your case, you're starting with the PE as the basis from which you're building this
Right.
whole, reproducible methodology, right? And that choice predetermines certain pathways, right?
It doesn't have to.
No, I totally disagree with you. Why does it do that? I just got done saying that we separate out the model from we separate out
The practice.
from the DCI, from the cross-cutting concept. So there's no limitation in there at all, Bob. Right? We separately unpack, and when we design curriculum, we separately put in different practices and different cross-cutting concepts. So there's no limitations. On the other hand, the argument that Izzy made is really important. If you want to get materials adopted in a school and have kids be able to do something, you have to be able to stand up there and say, we're building towards this. And in fact, what you would love to do, which we hope we're going to show because we're doing an efficacy study, that when you do this kind of work, compared to other instruction, kids actually do better on a third party.
Yeah, something we didn't create, somebody else.
Create that's supposed to be three-dimensional, right? That's what you want to do. If you want to if you want schools to change, you have to show evidence that it works, right? It's all a political process, right? So the development process is different than from where you're going to. And when you stand up and talk to administrators, as you should know much better than I do since you were one of them, you want to be able to stand up there and basically, so we're building towards this.
Because that's the language they understand.
Sure. But go back to your, so other people should chime in here because this is meant to be an open discussion, right?
Oh, you want this? Sorry.
Wherever your thing was. There you go. Excellent, right? So you start, the very top of the thing there is you're starting with a target performance expectation.
Yes.
Right, and that kind of determines your space through this whole thing, right? I get that Joe is saying, okay, well, we recognize at some point we pull in other things, right? But but that choice really does kind of determine how these other things flow. And I totally get that in the end you want to talk to administrators, but the administrators in hearing that are going to be just as happy with a post-op kind of analysis of this learning progression gets to these places. Right?
There might. I mean, I don't argue against it. I just think that maybe this figure doesn't do our process justice and how much we kind of really take into this account. And maybe we are kind of more geared to kind of presenting it in a way that people are expecting to hear standards. So maybe we should kind of revise it. But I agree with Joe. I think that these kind of 3 boxes here that actually expand it go above and beyond the initial point. So we go like this instead of like this. Again, I'm sorry, the PCA is the best example I could come up with.
So you have to realize when we either design assessment or design curriculum, we don't just take the one practice. We don't just take the one cross-cutting concept.
And no, we don't even take the one core idea.
DCI, and we're very carefully, again, Izzy wasn't trying to present our whole design model here, right? We very carefully developed a coherent sequence that will build until Melanie disappeared. We very carefully build towards some aspect, right? It's not like we're gonna get to this whole DCI. We just never do that. So this is probably, or the way, it's not a good representation overall.
Yeah, if you're thinking, yeah,
You see too much.
yeah.
Anyway, I could love to stay and argue with you, but I have another meeting. That's why I'm standing up to leave. Not because I don't want to talk anymore.
And I just want to go back to the. This. Go back. Okay. Thank you.
Come on, somebody else.